Now let's look at the cascade refrigeration system. Now this figure right here shows a two-stage cascade refrigeration system. So this system is very useful when you're looking to target low temperatures or when the cooling load is very high. And this will make sense in cases where, the temperature gap between TC and TH is so high that using a single compressor to, go from this P1 here to P6 here would be pretty work intensive. I mean, it would require too much work input to make the cooling load that's needed here. Okay, and the reason we say about TC and TH is because the compressor has to, pump is to compress the gas from a pressure P1 to a pressure P6 so that it's hot enough to reject heat to the environment. So for a lot of cases where we want to achieve very low temperatures or the temperature range is too large for given for a single compressor to be practical, uh, it makes sense to do cascading, right? Cascading is simply having two different refrigeration cycles, each cycle using a different refrigerant. So here we sort of make use of, we optimize the pressure temperature characteristics of the refrigerants such that we increase the COP as much as possible. Okay. Now, what exactly is happening here? So if you want to think about this in terms of the Rankine cycle, right? This is very similar to the binary cycles we discussed there. Okay. So here what we are doing is we are having two cycles, cycle A and cycle B. These two cycles have their own mass flow rates, m dot A and m dot B, and their own refrigerants. Okay, so refrigerant A and refrigerant B. Now, the cycles are similar. You have a condenser, a compressor, an expansion valve, and the evaporator for cycle B is replaced with a heat exchanger. Okay, so this is the place where this working for the refrigerant B is absorbing heat. Okay, so that's Qn for cycle B. Now it's absorbing heat from the bottom cycle, which is cycle A, and the cycle A is basically rejecting heat here. So this heat exchanger acts as the evaporator for cycle B and as the condenser for cycle A. Okay, so basically by using this sort of a system, what we are doing is we are breaking down the huge temperature gap into two. So here you have TH for cycle B and TH TC for cycle B. Now TC for cycle B, for example, is let's say 10 degrees Celsius. TH is about 40 degrees Celsius. Okay. Now TH for cycle A needs to be higher than this temperature because TH is sort of rejecting heat to that, right? So TH, let's say, is 15 degrees Celsius. Now, at the same time, we want to extract heat from something which is at very low temperature, right? So we want our target temperature, let's say, it's minus 15 degrees Celsius here. Okay, so you see by using these two different cycles, two different stages, we are able to reduce the temperature gap between TC and TH. Okay, so if you had one cycle, then you're talking about a temperature gap of about 55 degrees Celsius, which is too high for a single refrigerant to operate or a single um, compressor to operate, especially when you're dealing with larger cooling capacities. So here what we're doing is we're sort of breaking it down. So delta T of cycle A is about 30, right? And delta T of cycle B is also around 30. So this is how we are breaking it down and ensuring that we reduce the amount of work input that goes into provide the cooling. But you need to remember that the cooling is happening only here, right? There's no other place where the cooling is happening. So this is where we're achieving our desired objectives, and we need to provide some amount of work input. So since the mass flow rates are different, you need to be careful about that when you write this, the beta or the coefficient of performance of the refrigerator. The Qn happens only in cycle A, so you got to take mass flow rate of cycle A. The work input happens in two different cycles. Got to take the appropriate mass flow rates. Now, the whole reason why we bothered about doing this cascading is because cascading improves the COP of the system. For large industrial systems, any increase in COP is beneficial, right? It makes sense in terms of the economic cost. And although I'm showing you here two stages of cascading, it's very common to use three or even more, 3 to 4 stages of cascading, depending on what your desired TC is, right? What temperatures you want to achieve. Any questions here?
clear, Doctor.
All right. Okay, so this is a rather simple version of this of the modification. So I mean, here the mass flow rates are different, and if you want to determine, then you may have to apply energy balance on the intermediate heat exchanger. So there's a good example problem in the textbook. Have a look at this. Have a look at that. In the class, I want to solve the problem for the other case, which is the multi-stage compression refrigeration system. This is slightly complicated in the sense that here the mass flow rates are not equal in the same in all components. They are different. Okay, so we got to so I want to solve this problem and make it clear to you how to handle such a case. Now, in the previous case, we said we have two different refrigerants, right? Two different cycles, two different refrigerants, and we are sort of exchanging heat when a condo flow heat exchanger where the two refrigerants certainly do not mix, right? So they go through individual piping here and exchange heat. Now there are some cases where you can make use of the single fluid. You can make use of one refrigerant throughout, right? And you still want to use two compressors simply because you want to reduce the compressor work input, and the difference between P1 and P4 is very high. Okay, P4 is much higher than P1. So instead of doing it in a single compressor stage, which would require a much larger work input, we do what is called as multi-stage compression with intercooling, right? Same way as what we applied in the Brayton cycle. So here, the main difference in this sort of multi-stage compression refrigeration system is the fact that we're using the same refrigerant throughout. Okay, refrigerant remains the same throughout. And here, since we are using the same refrigerant, we replace the heat exchanger that we had in the previous case with a direct contact heat exchanger here. The previous case here, this was not a direct contact heat exchanger. This was some sort of like the closed feed water type heat exchanger, right? So here, the two fluids do not mix. So since here we just have single fluid, we go with a direct contact heat exchanger, which is simply like a mixing chamber, right? So you have two fluids, a hot and cold fluid, coming in from two different sides, and they get mixed. The reason we make use of direct contact heat exchanger is simply because the heat transfer characteristics are always better in a direct contact heat exchanger as compared to a heat exchanger where the two fluids are not directly in contact. They are not directly mixing. Okay, so when you're using the same refrigerant, it makes sense to do this sort of a thing. So before we go ahead and look at what's happening, let's look at cycles. Let's look at the cycle from state 3. Okay, let's start from here. So let me say the mass flow rate here is m.3. Okay, so you're starting from this point. Now 3 to 4 is the usual compression process. Nothing new there. That's what you do in every refrigeration cycle. So you reach here. Then 4 to 5 is constant pressure heat rejection. Okay, you're rejecting heat to the environment. That's Q out happening here. 5 to 6 is the expansion within the expansion valve. Okay, so this is we expand it such that it reaches an intermediate pressure. Okay, so the pressure after the expansion here, right, the pressure of state 6 has to be equal to the pressure of state 2, which is the exit of the first compressor. So let me call this as stage 1 compressor and this as stage 2 compressor. Okay. So why do we stop here? Why do we not go continuously all the way to down to this bottom pressure, the evaporator pressure? Well, we do that because we want to mix the two fluids, right? The two fluids, if they're mixing, they need to be at the same pressure. Okay, so let's come back to state 5. Okay, so we are at state 5. We do the usual expansion stuff. H5 would be equal to H6, and we reach at state 6. Now at state 6, what we have is a mixture. Okay, and we have liquid and vapor components. So we send it through a flash chamber, which is nothing but a huge tank, right, with two outlets, one outlet at the bottom and one at the top. Here we sort of separate the liquid and the vapor part. Okay, the liquid part obviously has higher density, so it collects at the bottom. So we have a valve here to open it, and all we get here is the liquid. The vapor part is the one that's remaining at the top, and we have an outlet at the top. We open it and we extract it. So what happens is that you have at stage 6, you have some amount of liquid, right? And that's equal to 1 minus x, where x is the quality. So 1 minus x times m.3. So this is the fraction of the mass flow rate that ends up being a liquid, and we send it through another expansion valve and down to the evaporator pressure. The remaining the remaining part of the refrigerant, which is a vapor, right? It has a mass flow rate of m dot 3 times x being the quality. We make use of it later on. We'll come back to it later. So let's go back and look at what's happening to state 7. So state 7 to state 8, well, undergoes expansion. It goes through an expansion valve, and we reduce the pressure back to the evaporator pressure. Now from 8 to 1 is where it happens, right? But the key point here is from 8 to 1, the mass flow rate is reduced. It's not m dot 3, but it's m dot 3 times 1 minus x. Okay, so you got to be careful about this. So this is the mass flow rate of the refrigerant as it goes through the evaporator, and then we compress it within the compressor. So it comes out as state 2. Okay, now this is an isentropic compression. Now, before we pump it further, we want to certainly cool it down, right? We have seen this before that when you cool it down, you're reducing the work input required to achieve the same pressure rise. So here we have something at a pressure P2, right, which is equal to P9, and at state 2 the temperature is higher than the temperature at state 9. So this vapor which we took out from the flash chamber, we use it to cool down the exit of the stage 1 compressor. Okay, they go through a heat exchanger, come out at S3. Now state 3 is basically somewhere here, somewhere in the middle, more closer to H9 maybe, depending on how much flow rates you're sending through it, how much depending on the value of X. And then once you are at state 3, you compress it further to state 4, and the cycle repeats. So the whole reason why we built this slightly complicated system with a direct contact heat exchanger and a flash chamber is simply because we wanted to reduce the compressor work input to achieve the same, let's say, cooling load. Now, let's say if you did not have two-stage compression, right? If you do not have two compressors, if you just compress from state 1 to state to pressure 4 in a single stage, then you would be going along this path, right? 1 to A. On the other hand, since we are sort of doing two-stage cooling with two-stage compression with intercooling, the path we followed is the green one. So you go from 1 to 2, 2 to 3, which is the cooling part, then 3 to 4. So by doing this, what we are doing is we are able to save some amount of work input. And the shaded area that I'm showing here is basically the amount of work input that we are saving by doing this multi-stage compression. So this is the same concept that we had in the Brayton cycle. Multi-stage compression with intercooling always reduces the work input required to achieve the same pressure rise.